for coming. So we have Sarah Caudill visiting us this week, and so Sarah's from Nikhef, but she did her PhD at Louisiana State University with Gabby Gonzalez, where then she moved on to University of Milwaukee, Wisconsin, where she did a postdoc for 5 years. She's also a member of the LIGO collaboration and more recently the Virgo collaboration, which is the Italian gravitational wave detector. She's also been, since detecting gravitational waves, she's been awarded the Breakthrough Prize for her work in the discovery, as well as the Council for Undergrad Research. And she's been at Nikhef for about 8 months, which is in Amsterdam, where they apparently have a nationwide obsession with mayonnaise.
Yes.
So she'll be talking to us about lessons learned in gravitational research.
Thank you. Yeah, so I guess a couple more of you have also gotten the Breakthrough Prize that was awarded to LIGO and Virgo collaboration. Yeah, so today I'm going to talk about the lessons learned in compact binary coalescence searches so far. So I'll tell you what LIGO and Virgo have analyzed and what our plans are for the next couple of months as we prepare for our next observing run. Okay, so just to outline, 01 and 02, those are our first and second observing runs. I'll give you a summary of that. I'll talk about the match filtering search pipeline that I work on and that made all of these the type of pipeline that make all of the detections, and then the stories behind each of the detections, and what we're doing to finalize the second observing run's data analysis, and thinking about 03, the third observing run, and beyond. Okay, so just a reminder, this was Advanced LIGO's first observing run. It was 5 months long. It started in September of 2015. It was only the LIGO detectors participating. So this was the Livingston and Hanford detector. As you probably know, we detected GW 150914 almost straight away after turning on and starting our engineering run. So that was very exciting. We had another marginal detection that looks very much like a signal, and in fact we kind of count it as a signal now in October of that year. And then finally, towards the end of 01, we had a second confirmed detection, GW 151226. So those were 3 binary black hole mergers, signals from binary black hole mergers that were found in the first observing run. That was just 5 months. And then we had our second observing run that started in November 2016 and ran all the way up to August of 2017. So a little bit longer than 01. And we had great success in this run. Another binary black hole detection in January, not long after we turned on. Another one in June. And then for the very last month, actually LIGO was going to turn off, but Virgo said, hey, we're about ready to come online. So LIGO ran a little bit longer and Virgo turned on at the beginning of August. And right when Virgo turned on, we had 2 amazing detections. 170814, which was the first triply detected binary black hole system, and of course the binary neutron star detection 170817. So Virgo was only on for 1 month, but had great success there. Okay, so that was the second observing run. All right, just a summary, a cartoon summary of all the binary black holes we've seen to date and their distances. LVT 151012, that marginal candidate, we think is the furthest one that we've seen, although the furthest confirmed is 170104 at about 2 to 3 billion light years away. 150914 is the most massive that we've seen, and 170608 is the least massive that we've seen so far. And then, of course, 170817, our binary neutron star system, very exciting. Confirmed signal, both in gravitational waves and electromagnetic counterparts identified. So this is a very exciting time for us. All right, so what about, oh, I should also say this was the closest signal and the loudest signal that we have observed so far, 130 million light years away. Okay, so what about the status of the detectors as we move from O1 and to O2, and what are we expecting as we go beyond that? So in O1, this is a plot showing sort of our sensitivity to a canonical binary neutron star system. So giving us the angle average distance that we could see a signal with a SNR, a signal to noise ratio of 8. And this is giving us the progress over the whole of the first observing run. There are only 2 detectors on, Hanford and Livingston. And if you average the range, or the distance to which we could see this canonical BNS system, was about 75 megaparsecs. If we look at the improvement when we move to O2, again, we see the same plot. For Hanford and Livingston, you can see if you average the ranges, you improve a little bit, so about 78.5 megaparsecs over O2. And you can see that Livingston significantly outperformed Hanford for the entirety of the run. And towards the end, you can see we're starting to peak above 100 megaparsecs or so for Livingston. So it was doing really well at the end of the run. Hanford, you can see, had sort of the opposite behavior here. It starts to drop off. I'll talk a little bit more about what happened there and the consequences of that. Here's Virgo. So Virgo came on only for the last month. So this time scale is just for 1 month here. And you can see it was pretty stable over the month of August. And it had a range of about 25 megaparsecs or so. So pretty good. All right. So let's talk now about the search pipeline that detected most of these signals. Okay, so the type of pipeline that finds binary black hole and binary neutron star systems is a match filtering pipeline. And I'm going to focus mainly on the particular pipeline that I work on, Heather works on. Some of you may know Kip Cannon, who also is a developer and inventor of this pipeline. It's called GST-LAO. So it uses G-streaming technology to stream gravitational wave data, like audio, basically. And it also uses LIGO algorithm libraries for data analysis of gravitational waves, combines those packages into GST-LAO to do this detection pipeline. And the idea is that we're looking for binary systems that have multiple parameters, but we compress the space that we're looking down into 4 parameters. So 2 binary objects. Each one has a mass 1 and mass 2. Each one will have some component angular momentum. But to simplify things even further, we look at the component of the angular momentum that's along the direction of the orbital angular momentum. Okay, so that's 4 parameters we're searching over, 2 masses and 2 aligned spin parameters. So you can see that represented here in this plot. This is a template bank plot. Each point in here represents a unique mass and spin combination that represents a unique waveform. So this is mass 1, mass 2, and then the colors represent the different allowed chi values. So for this lowest mass region here, we allow only low spins, and that would be our binary neutron star region, where the templates, each little point here is a template waveform. The templates for binary neutron stars fall here. Binary black holes in this region where we allow larger spins. And then in this red region, this would be the combination systems, so binary neutron star black hole systems. So the idea behind match filtering is that for each of these templates, you generate your waveform. You basically cross-correlate that waveform with your data, shown here in blue, to identify a hidden signal in your data. And the point is that when you sweep that template across your hidden signal, you'll get a peak in the cross correlation, or what we call a signal-to-noise ratio time series. So that's a trigger. That's our first indication that there's something in the data. But of course, that can happen for all sorts of things in your data. So you have to be more discriminating. So we employ what are known as signal-based vetoes. And the idea there is that we're trying to focus on the particular time frequency evolution of the gravitational wave signal that we're looking for. So these are just some example time frequency spectrograms. So we've got time on the x-axis and frequency on the y-axis. The labels aren't important, but what is important is the color scale here indicates some power at frequency and time. And you can see they have different structures. These are all different sorts of glitches that we might see in our data. The particular form that we're looking for the gravitational wave signal is what's known as a chirp, and you can see that here. It has sort of this banana shape. So this is increasing frequency and amplitude with time. So you can exploit that, looking for that particular type of shape to design these vetoes. And this is an example of one of those vetoes that you can design. So in blue, we've calculated the predicted signal-to-noise ratio time series. Given that we think we found a signal in the data, we cross-correlate the template with itself and add some noise in there and see what the expected or the predicted SNR time series looks like. We compare that against the measured in black and subtract the two. So it's like a chi-squared based test. If it's a true signal, it should be close to 0. If not, if it's a glitch that doesn't have that form, then you can get non-zero values. So that's just a different discriminating test that we can use. Okay, another important tool that we use in our pipelines is coincidence. So we have 3 detectors if everything's operating correctly. And we require that if there's a peak or a trigger in the SNR time series, that it should be within the light travel time of the different sites for each trigger. And so if that's the case, then we flag that and we store it as a possible gravitational wave candidate. So those go on to be further examined and vetted. But you notice there's other times when you might have a peak in the SNR time series, and it's not coincident with anything. In the past, those are just thrown away, not looked at. But with the GST-Lau pipeline, we actually store each of those and use those to make a background noise model. And I'll say a little bit more about that in a minute. Okay, so once we've got our candidates and we've got our triggers, we pretty much have all the information we need to compute a likelihood-based ranking statistic. So we compare all the parameters, the data parameters from Hanford and Livingston, and compare those against a signal model. And then we take those parameters and compare against a noise model and compute this likelihood-based ranking statistic. So as I mentioned, the denominators coming from this noise model that we're measuring from these non-coincident triggers. And the numerators coming from an analytic model, since we know a lot about modeling gravitational waves of this type and modeling their different sky locations and things. We can do this semi-analytically. Okay, so let me say a little bit more about that. So different components. So focusing on the signal model, this is the numerator. So for instance, one probability density function that might go into that likelihood ratio would be a model of what a signal to noise ratio, so a signal model SNR versus some signal-based veto, that chi-squared test that I talked about. And you can see the most support for signals falls in this region. We've got very little support out here for any real signals. So if we had a trigger come in and it had parameters that placed it out here, it would very not likely be a signal. Similarly, we can measure the delta T between triggers in the 2 detectors and plot that versus their signal to noise ratio. And we see that we have the most support in the region, for instance, where if the triggers have 0 time difference, meaning they fall, the source falls on a ring on the sky between the 2 detectors, then it's likely that their signal to noise ratio is the same in both detectors. So you could imagine a case where maybe we don't have equal sensitivity in both detectors, and this would not hold. So that's something we're looking at in O3 and not making that assumption. So that could actually be a problem here. Okay, for the background, so this is the denominator now. We took those non-coincident triggers. We can produce the same sort of probability density function. So this is again SNR and then the signal-based veto. You can see this looks much different than, let me just flip back. And this is our signal distribution. This is our noise distribution. So you can see now we've got sort of a structure where you can get very high SNRs, but those tend to have high chi-squared values as well. So this is the region where we would expect signal to be most supported, or for noise to not have much support. Okay, and then this is a movie. Let me just start it. So this shows that this is a static plot, but really we have to make this plot for all the different parts of the template bank. Because different regions, the longer the signal, the less background we have. And the shorter the signal, the more it looks like bursts of noise in the data. And so we kind of have to model this over a full mass parameter space of the templates. And so you can see how the background varies as we increase the mass. And so we start getting more and more triggers happening out here. So this is something that's tracked for all of the different masses. Okay, so let me just say a little bit more about the template banks. So this was the O1 template bank that we used. You already saw this one in the previous slide. I just wanted to point out that it had about 250,000 templates, and the upper mass cutoff here was about 100 solar masses. So not quite cutting into the intermediate mass black hole range. We actually had a separate search that kind of looked in the intermediate mass black hole range. So this was from 50 to 600 solar masses. So looking for binary black hole systems in those mass ranges. And it has quite a bit fewer templates here. So there were only about 45,000 templates that were done in this search. And they did not find any signals other than the binary black holes that were found by this other search. So they just confirmed that indeed there were binary black hole signals in the data, but they did not find anything new. This will be repeated in O3 and O2 as well. Okay, so moving to O2, we actually expanded our bank quite a bit. So now we've gone up to 400 solar masses. Now we have 677,000 templates, quite a bit more than we had in O1. And we've got a mass cutoff here, I think of 1 on 100. And you can see that we've got a special grid we had to place out here at the very highest masses because the template placement algorithm, it looks for places where your mismatch between the nearest template is greater than 3%. And it turns out that the mismatches out here are not very bad, even when it's very sparsely populated. So to force more templates out here, we had to place a special grid. And so that's why it looks much more regular out there. All the other templates are placed stochastically. Yes?
It looks like there's a ridge or something in the view.
Yeah, this one here? Yeah, so what happened was so if you ignore that ridge and imagine what the density would have looked like if you just extrapolate from what's happening here. That's what we originally had. And we realized that there were not enough templates out here. Well, there were enough templates to detect a signal, but there were not enough templates to properly capture the detector noise features. And so what we had to do was go in, starting right here, and overpopulate. Yeah. So it was not in order to catch more signals, it was in order to better capture the noisy templates and isolate those.
Sorry, it's probably a basic question, but why does simulations take longer for high masses? Which is why probably it's sparse, right?
Why does the what takes longer?
Is the reason why it's sparse at high masses because simulations take longer?
No, it's actually because the metric that it's used to place templates is not Euclidean. The metric measures the mismatch between the nearest template, and it requires that it be at least 97%. And out here, the metric is much wider. So it's a non-Euclidean metric that's used in the placement.
So at low mass, you change the mass of the waveform changes a lot. High mass,
Yeah.
you change the mass of the wave doesn't change.
Yeah.
So it's not simulation, simulation is basically.
How is it?
No, it's
Placed?
okay.
Okay. Yeah, so this is actually, the sparse placement out here is something we're looking into and trying to understand. Okay, maybe it's doing what we want, but we have to be careful about how we're detecting noises in the data and noisy templates in particular. And as we want to expand this space even further, what happens? So that's something that's currently and actively being investigated. Okay, and just for comparison, this was the line that we had in 01. So we've expanded past there. Okay, so we had to verify that things looked okay. So even after we made the bank, we did simulations. We injected signals into the data and tried to detect them. And so what we see here is basically the match of our injected signal population for binary neutron star systems. So this is an aligned spin parameter. So we're talking about this aligned spin again versus the total mass of a binary neutron star. So we've gone from about 2 to 2.5 here. So not very large mass range. But you can see all of them are pretty much red. So we're right at 0.96 and above, which we require 97%. So we've mostly achieved that. If we want to look at how our search does with more generic processing spins, so not requiring this alignment, we did that as well. So we injected a bunch of signals that had processing spins and looked at how our bank did at recovering them. And so here, this is from minus 0.1 to 0.1. So this is an even broader range than I've got here. So you can see it's doing pretty good at recovering even processing spins with pretty high match, up to 0.1 in magnitude. But beyond that, our bank does fall off. So if we have really high chi-effective, then our bank is not going to detect those types of neutron star systems. But that's expected. We didn't place templates out there. We can also look at neutron star black holes. And so the bottom here, the color bar has changed. This is 0.95. So this is 95% match down here. You can see we have very few, if any, blue dots. So for all neutron star black hole systems, our bank is doing a really good job at finding them with a nearby template. So we see similar results for the binary black hole systems as well. So everything was looking good, and so that's why we decided to call the bank final and move on. Okay, so I just wanted to point out a distinction between an online and an offline search, because I want to talk a bit more about online, which is also known as a low latency search. And for gravitational waves, when we talk about detecting candidates in low latency, we mean on the order of a minute or less. So for some scientists, maybe that's not really low latency, but for us, that's what we mean when we say low latency. And in that time, we can usually get a quick estimate of the significance, and we can also get an early sky map to send to electromagnetic partners. Now the offline search, which is also known as a deep search, because it has quite better data quality by the time it's run, will usually happen within a few weeks. So we'll have results weeks after we have made a detection. And it's a deep search because it utilizes up-to-date data quality and calibration information. This is information that comes in a couple of weeks after we've collected the data. And we usually use about 5 days of data. We collect 5 days, and then we analyze. And that gives us enough background to do a 5 sigma statement for a candidate, or a detection if we have one. OK, so just to point out, the actual bank that was running in O2 was not that full up to 400 solar masses, but it did have quite a few templates. It went up to 150 solar masses. So I just wanted to point that out, that we actually do things slightly differently in online and offline. But despite that, what I'm going to talk about next is that the online has actually been quite successful so far. And all of the detections to date have been made in somewhat of a low latency analysis. OK, so as I said, all reported events from O1 and O2, except for that LVT marginal trigger, have been found in somewhat low latency. So this is a plot I'm going to walk through for each of the detections. And it's showing you the latency for 2 things. The latency for, in pink, the time to Grace DB submission. So that's the time it took us to submit to the gravitational wave database, where we upload our data and first alert our scientists. And then also the latency to then send out a GCN alert, so a gamma ray coordinate network alert, to alert the broader community. So not just the gravitational wave scientists, but the broader astronomy community. And so we've got each of the detections, 1509-14 and 1512-26 from O1, and then the 4 O2 detections. And these lines here are, since this is a log scale, are kind of just denoting the 1 minute time period for latency, the 30-minute time period, and then 1 day. OK, so the first thing you might notice is an overall trend in the latency that seems to be decreasing, which is great. But even for our best, we still have over 30 minutes to submit that final alert to everybody. So we want this to get down to a minute or order minutes. But looking at O1, you can see both of those took longer than 1 day to send the alert out. So I won't talk too much about that, but basically what happened was we detected them in low latency, and it took us a little while to accept the fact that we'd made the detections and that they were what we thought they were, binary black holes. And so this latency of time from detection here, even at 1 minute, to then 1 day taking us to send the alert out, was due to our own vetting process. So this was human vetting time. And so that's been significantly reduced. But OK, so that's the story for O1. Now let's look at each of the cases in O2. So what's happened with the detections? And we'll start with 170104. So the first thing you might notice is that the time to submit to ourselves, the Grace DB submission, is quite long. So what happened there? It was quite strange, because if you read the paper, offline searches both found Hanford and Livingston triggers to it was quite visible and quite loud. So both detectors had triggers in them. It was a binary black hole detection. So what happened? Why did the online kind of take some time? Well, it turns out that they weren't found in an automated fashion. In fact, they were found in low latency only by visual inspection of the L1 triggers. So there were no H1 data available at the time. And so we didn't have an H1 trigger come through to spark that coincidence test that I talked about. Therefore, we didn't get an alert. Just by eye, one of our scientists happened from a different pipeline, PyCBC, happened to be looking at this time series and noticed that there was a peak in the signal to noise ratio. Just thought he should follow it up, and sure enough, it was a clear chirp signal. So just got lucky, and that's why it took so long. It took a visual inspection time. And it turns out the reason that Hanford data didn't come through, even though later we found Hanford data was fine, was that there was a problem in the classification of the Hanford data as being okay to analyze. So if you look at the time of when the trigger came through, what scientists hope is that we've gone through all of these checks, and we get to the observing check and it's green, and that means we're fine to declare detection during that time and that we're in observing mode. But as you can see for Hanford, at that time the calibration was all red, and therefore we could not enter official observing mode. But it turns out that was a mistake. This entire period was marked incorrectly, and therefore Hanford data did not come through. Okay, so that was a lesson for us. First, we should be careful about miscommunication about when we change something in a state of a detector and we don't alert the engineers. And also that the fact that we had one trigger come through, we didn't have two, maybe we should pay attention to one trigger coming through sometimes, so we don't require coincidence always. But we didn't catch on right away, as you'll see. Okay, so what happened with the next one? So 170608 happened in June, and you can see also the GraceDB time to submission was very long. So what happened there? Again, if you look at what the offline searches found, both detectors had very significant triggers in them, and in fact, you can see it clearly in Hanford. So why did it not come through quite as well in the online data? Again, it was found by visual inspection. So again, the same guy was analyzing or just looking at the time data as it was coming through and noticed again a trigger and thought he should follow it up. And so no H1 trigger was produced at this time, and so scientists weren't notified. So again, at this point we realized, okay, maybe we need to be a little careful about requiring coincidence for interesting triggers to come through. Maybe we should sometimes allow single detector triggers to come through and analyze them in an automated way, so we don't have to have people staring at these the entire day and night, trying to see by eye when something comes through. Okay, the reason Hanford was not on this time was that it was legitimately off for maintenance. And so you can see that here. This is, again, a time frequency spectrogram, but we're talking about order of minutes here. And there's this very clear excess power at about 20 hertz or so. So there was actually some data where they were causing noise at 20 hertz. You can see it also in the power spectral density. So Livingston was fine. You can see its normal blue noise curve. Everything was fine there. 240 seconds before, in gray underneath, Hanford was fine as well. But then they started injecting this 20 hertz noise, and you can see a sharp spike at around 20 hertz or so. So since we could clearly see the signal in Livingston, for all of our analyses, we just decided to analyze everything above that noise, since everything above that was fine. And so that's how we were able to actually do a coincidence analysis and get the 5 sigma detection that we knew this signal was. Okay, so now let's look at the triple detection. So this guy has the record for quickest time to Grace DB submission, so under a minute for us to know that there was a signal in the data. Yet it still took over 30 minutes for us to actually send that alert out. But I think actually this was the triple coincidence. So we found in Hanford, Livingston, and Virgo. We actually did have 3 triggers in low latency coming from Hanford, Livingston, and Virgo. So this, I think, was the most successful candidate as far as detection goes. Everything went pretty well. We had a clear detection. All detectors found triggers. Everything worked in low latency. And we just have to work a bit more on getting the GCN submission going. There was some discussion that happened in offline later. So if you examine over a longer time the SNR time series for Hanford, Livingston, and Virgo for this triple coincident event, you'll notice that Hanford and Livingston were pretty clean, but Virgo has some noise. It's because it's at a much lower SNR. So this is 4. The scale here is 14 and 8. So Virgo comes through at much lower signal to noise ratio. Things look noisier down there. And there was this glitch that happened just a fraction of a second later. So people had to address the question, was this glitch related to this trigger? And in fact, a lot of people spent time on this, modeling the presence of a glitch here, finding similar glitches in the data, understanding what the glitches affect before and after. And the consensus was that whatever was happening here, this noise, could not have caused this trigger. So this is why we were strongly convinced that the associated Virgo trigger that was here was actually associated with these triggers in Hanford and Livingston. Okay, and this was a great success. Of course, you know that when you add Virgo into your detector network, you can significantly improve the sky localization. So we went from over 1,100 square degrees on the sky if we just had Hanford and Livingston to 60 square degrees on the sky. So you can see all the previous detections and then the triple detections localization is much better. Okay, so let's look at our final binary neutron star here, 170817. Looks pretty good. A little bit longer time to actually find it in the data, but still within minutes or so. And time to GCN alert was pretty quick. In fact, it was the quickest because, well, we've seen a BNS. We need to tell the EM partners immediately to turn their telescopes and look. So this was very much motivation to send that out as soon as possible. Looking at this, you'd think everything went wonderfully well, but in reality, things were a little more complicated. It was the loudest signal yet. So once we analyzed everything in offline, it had a combined signal to noise ratio, if you looked at all those detectors, of 32, which was by far the loudest signal we've seen so far, and also the closest. And depending on the constraints you put on the chi parameter, the spin, the allowed spins, you find that it is pretty much significant with a binary neutron star system. Okay, so looking at that, you'd think the data was very clean. But in reality, this is what we saw. So you can see the nice, beautiful chirp signal coming in. And then right on top of it is this very loud glitch in the Livingston detector. And so in low latency, we actually had no Livingston detector, or no Livingston trigger come through because I think the time was vetoed due to this bad glitch. And also it happened that the Virgo data was down at the time. So we didn't actually receive a Virgo trigger either. So this binary neutron star system came through as one trigger again, just from the Hanford detector. And remember, for those other detections, that one trigger was found by visual inspection. So we learned our lesson. We allowed for one trigger to actually come through as an automated alert just in time to catch this. So thankfully, by that time, the single Hanford trigger had come through, was very significant, and we were alerted on a very short time scale. I'll mention that, so you notice that these plots look much cleaner. So they've actually modeled this glitch, and you can do a couple things. You can actually remove it by windowing it out, or you can model it and remove it. And so people tried a bunch of different things, and it was found very significant in all cases. Okay, the other thing that was very important about the signal, and one of the reasons it was so significant, was that a gamma ray burst was detected 1.7 seconds after. So interestingly, so that was Fermi that came through. And interestingly, Fermi actually almost missed their trigger as well. It turns out that right around the time of the detection, the satellite had just entered the South Atlantic anomaly. And so there's actually two regions where there's an excess of high energy particles coming that could damage the Fermi instrument. And so this first region, they turn off their large area telescope, the LAT, the main instrument. So the LAT had already turned off, but the GBM, the smaller gamma ray burst monitor, was still on. It hadn't entered this final region here. So luckily, the GBM was still on in this little time window, and we just happened to detect in low latency that gamma ray burst trigger. So that was very lucky as well. Otherwise, we would have had to wait over 1,000 seconds or so after the signal arrived to detect that very high energy early gamma ray radiation. The other satellite that found a gamma ray trigger was Integral. And Integral also had a slightly interesting detection story. So it was actually observing 170814, the triple, which happened 3 days before. And it was in an orientation where it was optimal for looking at that signal. And so it could only detect the BNS. It couldn't slew and turn in time to look at it. It could only detect it with an instrument known as the SPI-ACS, which is a spectral analyzer of some sort. But this is actually the shielding on, on the shielding on that spectrometer. So in a sense, it made the detection with an anti-detection, vetoing tool that it usually uses. It's shielding, which is more isotropic in its detection capabilities. But luckily, that was also successful. So that was close, but lucky. Okay. So let's look what we're doing now to finalize the analysis on O2. We're reanalyzing the data, and we're going to release a catalog paper as soon as everything's reanalyzed. So that's the goal. Okay, so I'll mention what we were waiting for, why we have to do the reanalysis. The LIGO observatories had a series of upgrades, as you know, after the first observing run. That's why O2 was more sensitive. And what the instrumentalists decided to do was to parallelize their learning about the new challenges of each hardware upgrade. So Hanford decided to focus on an upgrade that would increase the amount of laser power and the cooling system of that. And it turned out the cooling system causes noise. And that, as we'll see, was the main reason Hanford actually had some serious noise issues during O2. Livingston decided instead to focus on the upgrade related to ameliorating scattered light and electronic noise. And that turns out to be maybe the better. They were luckier in that they didn't have to deal with some serious noise issues. Okay, so let's see what happened with Hanford here. So you can see, again, the BNS range plot where Livingston has significantly done better over the whole of '02. And Hanford has actually lost significance towards the end of the run. So as I mentioned, that higher power laser, they had to have cooling, and so that had water running on the table, and that caused serious vibrations on the laser table. So you can see the amplitude of those vibrations on the laser table were much higher at Hanford. So that's what they were dealing with. They also encountered another problem. There was a distortion in the optic at Hanford that was actually off-center and caused a heat source. And so usually they can compensate. They have a thermal compensation system. But if it's off-center, it's very hard to do in real time. So this was something that they couldn't deal with right away. For comparison, this is what the Livingston optic looks like. There's no point source, point absorber, and this sort of pattern, which is centered, can be dealt with the automated thermal compensation mirrors. Okay, so just to summarize the issues that Hanford was dealing with, in blue, you can see for Hanford and Livingston that's the total noise of each of the detectors, and then the different noise sources. So for Hanford, you can see obviously this purple curve, which is the beam size and motion, which was affected by that point absorber, which caused the beam size and motion tracking to not be as good, was really a significant source of noise that wasn't a problem at all in Livingston. Also in blue, length controls, well, that was about a little bit more. We've got angular controls and also power mains. Those are present in both detectors, causing the lines that you see at 60 hertz and its harmonics. So really it was this beam size and motion issue that was related to that point absorber that was really causing problems. Okay, so what are we doing about it? In fact, this is work led by Jeannie Driggers and a bunch of others. Basically doing noise subtraction. So if we can model the noise at the Hanford detector, we know a witness for that noise. So some monitor that, for instance, monitors the noise on the laser table, and then we understand how that couples to the gravitational wave channel. We can model that and subtract it from the gravitational wave channel. And so they did that, and you can see the improvement. So in blue is what we had before. In red is what's the noise has gone down in Hanford after the noise subtraction. And so we'll get about a 20% improvement in sensitivity in Hanford in our reanalysis. So that's significant, and that might lead to some interesting results. They also did the noise subtraction in Livingston, but it had significantly less effect there because there weren't as many problems. Okay. So thinking about '03 and beyond. All right, so the start for our third observing run is expected in fall of 2018, so not far from now. And we'll run for 1 calendar year. The LIGO detectors are expected to come in at least 120 megaparsecs or so. And that's the goal. So we're going from, I guess, late design here. Is that right? Do 2018? Yeah. Somewhere in between here is our goal. And Virgo, the goal is to come in at least 65 megaparsecs. So that's pretty good. That's almost approaching what the LIGO detectors had in '01. I can say a little bit more about, oh yeah, that's the late. I can say a little bit more about Virgo. So Virgo has actually had quite a few plans for new hardware. They're looking at installing new monolithic suspensions, so a new mirror system. a higher power laser. Also looking at doing squeezing to bring down the high frequency noise. And in fact, they were given a squeezing table from the Albert Einstein Institute for free. So they're already looking at installing that, and it might actually happen for O3. They've also done quite a bit of investigation of Newtonian noise sources. So these are local gravity disturbances in your area caused by massive things around you in your environment, and subtracting those out. So that can be really good at subtracting fundamental low frequency noise. And so their goal is to do double the current best binary neutron star range, so about 60 or 65, like I said. But if they can get the monolithic suspension technology set up and running, it could be up to 100 megaparsecs before the end of O3. So that's very optimistic, but if that's true, then we will have a very, very powerful 3-detector network in O3. Okay. So assuming we'll have, on the lower end of the sensitivities, what are the detection predictions for O3, given that will run over 1 year, and given certain assumptions about binary black hole, binary neutron star, and neutron star black hole systems? It turns out that if you make those assumptions and about the sensitivity of O3, then the median number of binary black hole detections will be about 30 to 40. The median number of binary neutron stars could be anywhere from 4 to 9. And even though we haven't seen one yet, we would be expected to see maybe 1 neutron star black hole system. So we need to really prepare for a large number, compared to what we'd seen before, number of detections in O3. Okay, so I'll end there, but I just wanted to say that we're currently redoing a reanalysis, so stay tuned, because you could yield new gravitational wave candidates, or at the very least, maybe interesting things about the candidates we've already seen. And O3, as I said, will debut the most sensitive network so far. It also turns out that CAGRA, having seen the success of Virgo in O2 without a huge amount of sensitivity, has been very inspired to come online in O3, even if they're not very sensitive. So there's a possibility that we could have a 4-detector network in O3. As I said, we could have dozens of binary black hole detections, a few more BNS detections, and possibly even a neutron star black hole. And we'll definitely look at doing new searches over uncharted spaces, so new types of higher mass searches, processing searches, all kinds of things. So stay tuned. Thank you.
Are there any questions for Sarah?
So you mentioned a few ways that you could miss a signal for various reasons, like things not being turned on properly, or
Yeah.
things like that. Is there an effort to model all of those things? Because I was thinking, do you need to understand the completeness of the survey if you want to talk about these objects as a whole population? How much do you need to understand all these various effects?
So the rates calculations that are done to try to understand, what is the astrophysical rate of binary black holes, for instance, given what we've observed, is very careful to try to only include what we have actually observed. But there is the possibility that, like what happened with the first two in O2, that we could find detections in times that we wouldn't actually have analyzed otherwise. And so handling that extra time, that's a tricky issue. And people are, luckily right now, we're not in a regime where that will significantly affect our understanding of the astrophysical rates. But yeah, I mean, one thing people are looking at doing is actually just analyzing everything, regardless of whether it's good data or not. And then we'll know the full possible amount of time that we could have found signals in. We'll find a lot of junk, but we can visually remove that by eye, or just say that the parameters don't look right. But yeah, we're not in a regime right now where we feel comfortable doing doing that with our search pipelines, but something to explore for sure. Yeah.
But it's not a limiting factor on the current estimates of the rates, I guess?
Not currently, no, but it will become an issue soon. And we're hoping to train our pipelines to just understand, this is bad data, analyze it, but rank it accordingly. And that way we just analyze everything and not have to worry about what happens if someone finds something outside of something we've officially observed. It gets complicated. Yeah. I don't think so. Have you looked into that? Yeah, I think it's well understood that it's just outside of the LIGO band. It would be more a LISA source, I believe. ET, yeah. Yeah, but with the current detectors and their future final design, I don't think that we'll be able to reach that source, unfortunately. But LISA's supposed to launch in 2034, so.
You'll still get one.
Yeah. Some of us will. Yeah.
That's the theoretically minimum latency you can keep. So your goal is 1 minute to hold up. You increase that.
Yes, it's a good question. So the matched filtering process will take longer the longer the signal is, just because the highest, you could, okay, so people are talking about doing early warning. If you have a long binary neutron star signal coming in, you can start to build up signal to noise ratio and even get a significant trigger before it merges. So you kind of have an early warning that the signal's coming in before the merger happens. So in that sense, you could have something possibly even before the merger. But you still have to consider maybe the time that it takes to do that analysis. And right now, I think we're on the order of minutes or so to analyze the data as it comes in and upload. So there are some algorithm enhancements and new efficient methods that can be used, but it will take a little time. But I think 30 seconds to a minute for match filtering, possibly looking at other algorithms that don't use match filtering could be quicker. Yeah, so as for the theoretical minimum, I don't know, but I'd say 30 seconds might be the best we can do right now for the algorithm. But as I said, you could get early warning with a very long BNS signal, even before the merger.
Who's that guy that finds all these things?
His name is Alex Nitz. He was at AEI, and yeah, so I guess he knew that. Well, I don't want to say the story, but I think he knew that one of the detectors was down, so he knew he should be paying attention, to the single detector data coming in, and so. I think he did.
Maybe use like cosmic low latency